Welcome back for the online class. Let us continue from the previous class. Now in the previous class we were discussed on like first order derivative, second order derivative, based on which how the transition of a pixel's value will be changed and how the response will be obtained. It is in the form of like a step, it is in the form of like a ramp. Okay. A ramp in the sense the continuous change. If the pixel values are all stable, means constant, you will get a 0. Okay. Similarly, in the today's class, we will see how the applications can be used for the purpose of image operation. It is as good as what we say is a smoothing, the smoothing of an image. What do you mean by smoothing is nothing but it's a type of like a filter operations. Okay. In fact, it is a spatial filter operation. The purpose is used for image blurring. Okay. Sometimes it is required to blur the image for the purpose of operations and also to remove the noise. Okay. Why we use a blurring? Okay. Let us take that. For an image of a person, let me consider if I took the face image of a person and you are interested in only the eye portion of a face, in which we need to blur the other portion and we are the interested part to be extracted. Before we extract, we need to blur the image. Okay, that is the object of interest to be extracted from the image, it is required to blur the image. Okay. Since it is a spatial filtering in which we are using with a box filter, also called as a kernel, window with many names, and equivalently we can operate in frequency domain also. Okay. For the image smoothing, just a simple example or a simple application we will consider is averaging. Okay. Now, how the averaging will be performed? Let us consider an image of which I will take a 3 by 3 pixels of a samples from the image. Okay. Now, if I consider a 3 by 3 from which I have extracted, the image size can be like a 500 by 500. It may be like, it may vary with a high number of pixels. I am going to be performing step by step operations, of which we will consider the first 3 by 3 pixels of an image. Okay. If you consider 3 by 3 pixels of an image, okay, we will average it out. Means all the pixels will be getting added and we will divide with a 9. What is the answer we will get here? Okay, let us take that. If I consider the center pixel value, okay, like this. Okay. Now here 2, 3, 1, 1, 1, 1. Okay, 1, 1, 1 randomly. I'll take it with the randomly. These are the center pixel. These are the box I consider. You just add it out this all. Okay, means 2 plus 3, 5. 6, 7, 8, 9, 10, 11, 12. Okay. Now 12 divided by 9. Okay. Now what is the value you are getting here? Okay, you are getting something like 1 point something, 1.3 something. Okay, because you are not supposed to be represented with a fractional value. You will be rounded with a 1. Means the center pixel value will be replaced by 1. It is already 1. Now it is replaced with a 1. Okay. Now if I change it. Okay, let me take, okay, I'll change with this value. Okay. Okay, 4, 5, 2, 3, 1, 2, 1, 2 and 2. Okay. Now, you just make an average of this. 4 plus 5, 9, 9 plus 2, 11, 11 plus 3, 12, sorry 11 plus 3 14, 15, 17 plus 5, 22. Okay, 22 divided by 9. Okay, what the value you get here now? Now you are getting something like a 2.5, 2 point some value. Okay, but 2 point value. Okay, now what is the value of center pixel here? 1. It is now replaced with a 2. Likewise, you need to be perform it for all the pixel value of an image. At the end, you will be come up with like a result that will be like a image will be smoothed out. This is what we use, what we call is the averaging of a filter, averaging kind of operations. Okay, it is the most used application for the purpose of image pre-processing steps. Okay, since it is also used for like edge blurring. Okay, I hope you understood this one. Okay, now I consider 3 by 3, just move it right side by again right with a one column. Okay, you process it for all the n number of pixels except the boundary of an image, you will be end up with the answer. That is a smoothed average filter operation. Okay, I hope you understood this one. Okay, now for the purpose we are using with like a box, also we call it a window box. Okay, all the same similar name. Means the earlier your image will be represented with F here, now it will be multiplied with a W. This is W is nothing but a box or a window. Okay, this W I have represented with a 2, 1 with like a all the 3 1 1 1 1 1 divided by 3 divided by 9. Okay, there is a one cross verification you can do by adding all the 1 1 1, you will be getting here 9. Okay, that is what the operation of a box means. This box will be multiplied with the image, and after the operation you will end up with like a one answer. That answer will be replaced with the center pixel of the image, not the full image. You need to be processed for the throughout the image. Okay, throughout the image. Likewise, if you perform, you will end up with a smoothed image. Okay, for this we are using a box with 1 1 1 1 1 1 1 1 1. The total will be 1 9. One more box you can use. Okay, that is a 1 2 1 2 4 2 1 2 1 2 1. Okay, if you added up this all, you will get here 16. So then 16 means this W will be multiplied with F, and whatever the answer you are getting, that will be divided by 16, and that answer will be replaced with the center pixel value. This is what the operation here. Okay, what the operation we are doing it for the purpose of smoothing of an image. Okay. Okay. There is the next filtering we are using is a order statistics filtering. Okay, the order statistics filters. Okay, there like many will be available, max, min, and the median. Okay, these are all non-linear spatial filters. Okay, why we call it a non-linear? Because the linearity from the output what we are getting here, okay, is not in the defined way. Okay, since the output is based on order of the gray levels in masked area. Okay, that is what median filtering, max, and the min filters are the statistical filters. Okay, we will see how the median filtering will be operated and how the max min will be operated here. Okay, and usually it is effective for like to remove the salt and pepper noise. Okay, the salt will be okay. Now salt and pepper, you can correlate. Salt will be with a white, means if there is the corresponding pixel with a high value of a white, it is called as salt noise. If it is with a low level of a pixel value, okay, means it is a gray, means it is a pepper. These are, if the more the salt and pepper noise for the image may not be clear. Okay, to remove this one, we are using with the order statistics filters. Okay, now let us take the simple median filter, how we will operate here. Okay, now for the image I got here, okay, 3 by 3 pixel. You may have with a 5 by 5 also. Now you write down this all the values, okay, in increasing order. Okay, all these values. Okay, now what is that here? Okay, now increasing order, I will write here 10 of this only, of the 9 by 9, which is the smallest value 10. The next increasing value will be 15, The next will be what? This will be done, this is done, okay. Now this is done, 20, okay, this one done, 20. You have tried the same value also, because I need to be capture all the values, okay, 20, okay. The next, this 20, next 20, okay, next 25, okay, next 100, okay. Now how many are there here? Total 9, okay, which is the center of this, okay, means from this one 4, from this one 4, what is the center value? 20, means what is the value of the center value of this one? Now 15, it will be replaced with what? 20. Okay, I hope you understood this one. Now what is the earlier center pixel value will be 15, now it will be replaced with the 20, because which operation you are doing? Median filtering. Okay, what is that here? You write all the pixel, okay, the pixel value. Only you are considered 3 by 3. You are not considered 500 by 500 pixels here at a time. You need to be considered immediately. There's the first step of this one, 3 by 3 pixels of an image. You write down in increasing order. After increasing order, whichever the middle value will be coming here, that will be replaced with the center pixel value. Again, what you do, if the image will be like something like, again there is a, sorry for this, okay. Now if there is a image, will be again the value, okay, like 5, okay, 15 will be there, 20 will be there, 30 will be there, 40 will be there, 50 will be there, and 100 will be there, okay. Now what you have to do, you need to be consider this, okay, this is replaced here, okay. Now you have to take this one, okay. Now in the first order and the second order derivative, the dou of x, dou f divided by dou x, okay, is equal to f of x plus 1 minus f of x, okay. It is already given. F of x plus 1 is the next pixel value, f of x is the current pixel value, and dou square f by dou x square is equal to f dash of x plus 1 minus f dash of x. If you open it out, okay, if you open this one, okay, that is f of x plus 2 minus f of x plus 1 minus f of x plus 1 minus f of x, okay. You just open all the bracket, you will end up with this equation. Okay, I hope in previous class I have used this equation for the purpose of spatial filtering. Okay. Now let us move. What is the necessity of using? Okay, there is a first order derivative and second order derivative. The first order derivative generally produce thicker edges in an image. Okay. Now how do we differentiate here? Okay, look at this. This is a thin image. If I make it, this is a thicker image, okay. That is f dash generally produce thicker edges in an image, okay. This will be a thicker edge, okay. F double dash have a stronger response to a file detail, okay, means fine, there is a fine details. If you want to obtain the fine details of an image, let us take that if you are interested in the features of an eye from the person you have captured, the fine details need to be extracted very clearly, and you can operate with most of the applications, okay. Now f dash generally have a stronger response to a gray level step. F double dash produce a double response at the step changes in gray level, okay. That is what f double dash will be multiple, there is a twice operation we are performing, okay, as I discussed in previous class, okay. Since f double dash responses given similar changes in gray levels values line, that is point is greater than step, okay. Since for image enhancement, f double dash, there is a second order derivative is generally better suited than f dash. This plays a very important role for your purpose of your most of the operations in your for your project, okay. Why we require a single dash? That is a first order derivative and second order derivative. Okay, the major application of f dash is for edge extraction. Okay, edge extraction, f dash is used together with f double dash results in impressive enhancement effect. Okay, I hope this slide plays a very important role for the purpose of your applications. Okay, to understand why we require the first order derivative and second order derivative. Okay. Now in the previous slide, I made a Laplace equation. Okay, what we call is a second order derivative. Okay, the Laplace equation will be given with a dou square f divided by dou x square plus dou square f divided by dou y square. Okay. Now, if you open the bracket, okay, because it is a second order derivative, this is second order derivative. Since the second order derivative dou square f divided by dou x square, it is along the x axis. Okay, that is what we consider along x axis, that is a x plus 1 y along the x axis this way. Okay, this way. Okay, now along this way with respect to x axis, because already I told it is x axis. Okay, but it is minus 2 f of x y with respect to this one. Okay. Similarly, for dou square f, the differentiation with respect to y, okay, along the direction of this way, because y is represented in this fashion. Okay. Now you substitute both the equations into the above this equation, you will end up here. Okay, the final answer in this fashion. Okay. Now look at this one. What is the answer you obtained? Okay. Each coefficient will be replaced or written in the form of like a box. Okay. Now this is my center pixel. What is the coefficient of that? Minus 4. Coefficient will, okay, f of xy, its coefficient is minus 4, right? Minus 4. Okay. Now there is like, I will come to this one, f of x plus 1 comma y. Okay, which is f of x plus 1 comma y? This value. What is the coefficient? 1. Now it will be replaced with a 1. Okay, f of x minus 1 comma y. What is the coefficient here? 1. Okay, that is f of x minus 1 comma y. F of x minus 1 comma y. Okay, this one, it is 1. Now similarly I will go with this one, the coefficient values. The coefficient value, this one. Okay, only I'll get here the first one, second one, third one, fourth one, and the middle pixel. The rest, whatever the values are there, you don't have any coefficient here. You have to make with the zeros. And whatever the box you are obtained here, okay, is a Laplacian box filter or a Laplacian enhancement filter. It is a standard filter what you obtain. Like early in the previously, I multiply with the f with the w. Okay, this w I have obtained. This, what is the Laplacian coefficient? This is the Laplacian coefficient. You can increase it here. If I increase it, if I make it with a 2, okay, there is one more cross check you can verify. Altogether you add up, you should get a 0. Right? If you add all the values of the box filter, you should get a 0. Means if I make it 2, okay, for example, if I make it, this will be 2, this is 2, this is 2, just simply without calculating this one, what the center value will be? Minus 8. Okay, that is this is what we call as a Laplacian box filter. Okay. Now since whatever the answer, okay, in the previously I obtained here. Okay. Now here one more the operation here, what we call is isotropic. This will be, let us consider it is a 90 degree what we consider. Okay, 90 degree because what you are finding, okay, along the changes in this direction. Okay, if I want to make a changes in this way, okay, it is in 45 degree, because what the changes you are measuring it along the vertical, there is a up, down, and the right and the left. Okay, now the change will be in a diagonal way, it is a 45 degree. Now isotropy, if the changes will be in a full day, it will be rotated for 360 degree. Okay. Now this is what the Laplacian, okay, box filter what you obtained. There is a one cross verification. Okay, it is a standard equation is obtained from the Laplacian equation. You need not change it here. There is a one cross verification you can do. After adding this one, you should get with a 0. This is also 0. You can verify this one. Okay, now for the positive response, if I make a 4 here, the rest all this will be -1, -1, -1, it will be 0. Now similarly, there is a inverse of this one, 8, 0. Okay, I hope you understood this one. Okay, how I obtained the box. Okay, this all the way I shown with the corresponding equation, how we obtain this box, and similarly the replicated box will be operated. Okay. Okay, this is what the application where we are using the Laplacian. Okay, there is a Laplace operator. There is especially for the image edge extractions. Okay, it will be thinner or it will be thicker. Okay, I hope you can see. Okay, it is visible for you. Okay, now look at this one. Image of the north pole of the moon. Okay, Laplacian filtered image, what you see is this B. Okay, now this will be like A, this will be B. Okay, this will be like C and D. I'll come to this one. Okay, image of the north pole of the image, okay, of the moon. The Laplacian filtered image. This is the Laplacian filtered image. Okay, sorry for this. Okay, this is the Laplacian. This is a Laplacian filtered image for the display purpose. Sorry. Okay, filtered image. The Laplacian image scaled for the display purpose here. Okay, I hope you can see what the difference you get here. Okay, from this image, from the second image, I'll go. This is my first image, A, B, C, B and C. I hope you can find the difference of this one. I hope you can see there is in the boundary very thin. You're interested in the boundary of the image very thin, so that we are using a Laplacian. Okay, since for the C, the Laplacian image scaled for the display purpose. Okay, similarly for the D, I hope you can see very much clarity you will obtain. Okay, for the enhancement. Okay, what I say, there is a most useful application what we use for the like image is the image enhancement, wherein which it plays a very important role of a Laplacian. Okay, since by distinguishing the features or a smoothness what we have obtained from the image, okay, the corresponding Laplacian has been used. Okay. Okay, this is also one more application you can apply, or you can use the Laplacian. Okay, Laplacian image enhancement. Okay, it's a 5. Okay, in the previously I told with the 0. Okay, now it will be not a 0 exactly here. Okay, there is like a 1. Okay, additionally you will be getting a +1. Okay, additional, because all -4 + 5 you are getting here 1. Okay, there is one more box you are getting. Similarly for this also you are getting here 1. Okay, and that is what the image enhancement operations what we are obtained. Okay, these are the applications, or you can visualize the clarity, how the clarity of the image or a smoothness in the image is coming out. Okay, by applying a image enhancement technique. Okay, I hope you understood the concept of Laplacian and the purpose of application. Okay, where it is the most suited. Okay. Okay. Now this plays a very important application for the image filtering, okay, smoothing to extract like a thin image, thick images, okay, and for the feature extraction of an image plays a vital role for the most of like image applications. Okay, since this will be the most useful technique for the image. Thank you.